Okay, in this slide we are going to add this AC source to the RLC circuit. You know, the RLC circuit, we learned that it was quite difficult, right? And we are adding one more component to the circuit in which the potential changes as a function of time. So it's going to be difficult. So therefore, in order to help you understand it, we are going to separately investigate RLC together with the AC source, and then later try to combine them all. Okay. So we have an AC source which looks like this in the symbol, and it has the potential amplitude Vm, and then this potential changes like a sine function, and then this frequency or driving frequency of this source, and we call it omega d. Okay, so our task is finding out what will be the current in the resistor. So in order to find the current, we use the voltage law. Okay, so we add up all the potential difference and it has to be 0, right? So how do we do that? Okay, we first come across this EMF device, so therefore plus V EMF, and then we go through this resistor along the direction of the current, so therefore it's minus VR, which is the voltage across the resistor. And then of course V EMF, we already have it here, so therefore simply write it this way, and then it becomes 0. So therefore the voltage across the resistor will be simply Vm sine omega dt, which is actually the same as the potential supplied from the EMF device. Okay, and then this is actually the voltage across the resistor, so therefore this amplitude of the potential becomes the amplitude of the potential across the resistor, so let's call it VR. Okay, VR is in fact same as Vm in this case. And then how do you get the current in the resistor? Simply divide the potential by the resistance. Okay, and there's nothing more than that. So therefore, now current in the resistor has the again has the same sine functional form, and then its amplitude will be VR divided by R. Okay, so because this is the amplitude of the current, we can call it IR. Okay, so what we learn from here is that when the driving AC source has the time dependence like sine function, then the across the resistor the potential will also have the sine function, and then the current will also be the sine function. Okay, so we can actually draw the graph to take a look at it. So in this graph, the horizontal axis is the time, and this blue curve, this red curve is the potential, and blue curve is the current. And of course they have different amplitude because the current and potential are not the same to each other, but they exactly follow each other. So when one is maximum, the other is also maximum, and one becomes 0, the other is also 0, and they are exactly moving together, right? So therefore we can say in the resistor the current and potential are in phase with each other. Okay, and next, how about the case of capacitor? Okay, now here we have this EMF device and the capacitor only. So in order to know the current in the capacitor, we again use the voltage law. Okay, so using the same voltage law, we already know that the voltage across this capacitor is actually the same as the voltage across this EMF device. Okay, so now we can write it this way. And then from the capacitor, we actually learned that this voltage across the capacitor is directly related to the charge in the capacitor, and then the proportionality constant is the capacitance, Q equals CV, right? If you remember it, then you can figure out that the charge in the capacitor actually also changes by the sine function, right? Okay, so from here, how do you get the current in the capacitor? Can we divide the potential by the resistance? But there is no resistance. So therefore, what we have to do is we take the time derivative of the charge. Then we will get the current, right? You know this. So therefore, when you take the time derivative of this guy, this omega d will come out like this, and this sine function will change to cosine function. Okay, so from here we know that when the voltage across the capacitor is the sine function, then current across the capacitor will become cosine function. Okay, interesting, right? So we can draw a graph like this. Again, as a function of time, this red curve is the potential, which looks like a sine function, and this blue curve is the current, which looks like a cosine function, right? So when the potential is, say, 0, then current becomes maximum, and when potential becomes maximum, then current becomes 0, and then next, when potential becomes 0, and then current will become minimum, which is actually minus maximum, and then when potential becomes minimum, then current will become 0, and so on. Okay, so which means they are not in phase, they are shifted from each other. Okay, and then actually from the high school mathematics, we know that cosine omega dt must be equal to sine omega dt plus 90 degree, right? So if you compare this sine function, if you compare this sine function with this sine function, now we know that the current, the angle of the current is 90 degree larger, right? So it means that in the capacitor, current is 90 degree ahead of the potential, or 90 degree faster than the potential, or in other words, the potential is 90 degree behind the current. Okay, this is how it is. And at the same time, there's one more thing. Okay, now we have a current here, and then the potential here. So therefore, we know how the potential and current are related in the resistor, right? So therefore, in this case, this quantity is not actually a resistor, but it's actually similar to the inverse of the resistor, right? Okay, so if you, in this case, if you write it this way, this XC here, XC is not the resistor, but it kind of works like a resistor in the case of alternating current. So therefore, we call it capacitive reactance. And then this capacitive reactance is equal to the 1 divided by omega dc. And then, of course, this quantity is meaningless if you have a AC source. I'm sorry, if you have a EMF device which is not changing as a function of time. This capacitive reactance works like a resistance only if you have an alternating current source. Okay, this is what you have to remember. And finally, in this slide, we will study the case of this AC source with the inductor only. Okay, again, we are going to use the loop rule, and then we get this equation. So EMF across the potential minus the EMF across this inductor finally becomes 0 following the loop rule. And then what is this potential across the inductor? Actually, if you go back to chapter 30 and look for the part of the RL circuit, we already had this expression, which is given here. So potential across this inductor is equal to the inductance multiplied by the time derivative of the current. This actually comes from the definition of the inductance. Okay, so here finally we want to know this current in the inductor. Okay, so how do we get this out? Now this is in the differential form, so therefore we can rewrite this so that the small this current in the inductor is actually equal to the VEMF divided by the inductance multiplied by the small piece of time, right? And then, of course, this VEMF follows the sine functional form. So all we have to do is we just have to integrate this to get the current in the inductor, right? So we are doing the integration. So what we have to do is that we have to integrate sine function. And then what do we get? Actually, since we are integrating the sine, this omega d will come out as an inverse. Now we are doing integration, which is reverse of the differentiation. And then this sine becomes minus cosine. Okay, this is not just cosine, this is minus cosine, because if you differentiate cosine, it will become minus sine. So therefore, you need the minus sign here. Okay, so then what we get? So again, using this graph, in this graph, the red one shows you the potential, which originally followed the sine function. And then now this time, the current will be minus cosine. So minus cosine looks like this. It's cosine reversed, right? Okay, so again, now current and potential are not in phase, so they are shifted away from each other. And then let's take a look at it a little bit more closely. Again, from the high school mathematics, this minus cosine is actually equal to sine omega dt minus 90 degree. Okay, so therefore, the angle of the current in the sine function is actually 90 degrees smaller than the angle of the sine function in the potential, right? So therefore, in this case, we can say now current is 90 degrees behind the potential, or in other words, potential is 90 degrees ahead of the current, which is exactly opposite to the case of the capacitor. Okay, and then again, we have the current here, and we have the potential here. So therefore, this part is again similar to the resistance. I think in the previous page I said the resistor, but I meant the resistance. Okay, so therefore, actually this is not exactly a resistance, but this appears like a resistance when you have the inductor and the alternating current source. So therefore, we call it inductive reactance, and then this quantity is actually I forgot to write XL. Okay, so this part is actually equal to VL divided by XL, just like in the previous page. So this XL is equal to omega DL. Okay, so what it actually means is that how about the direct current, which means the constant potential? If we have an EMF source with constant potential like a battery, omega D will be 0, which means that in the inductor there will be no resistance or no reactance. But if you have a alternating current source which changes the potential as a function of time, if it changes quickly, then it's like having large reactance. Okay, and this is exactly opposite to the case of the capacitive reactance. Okay, so here I'm going to make a summary of the 3 cases that we have discussed in the previous 2 slides before finally making real combination of the RLC. Okay, the first case, the AC source and the resistor, the voltage or potential in the resistor, and then the current in the resistor, they were in phase. If one has the sine functional form and the other will also have the sine functional form, and then the resistor was directly obtained by dividing the potential by the current, and it was also equal to the amplitude of the potential divided by the amplitude of the current, right? Okay, and then again they are in phase, and in order to see that this current and potential are in phase, now we will in this case use something called the phasor instead of the sine functional graph. Okay, so the phasor is something like this. You imagine an arrow or a stick, and suppose that one end is fixed at the origin, and this arrow will rotate counterclockwise at the certain angular frequency. And in our case, this angular frequency will be, of course, omega d, which is the driving frequency of the AC source, right? Okay, and then it will continue to rotate as a function of time, and actual potential, actual value of the potential we will measure will be the projection of this arrow along the y-axis here. Okay, so at this location, this much will be the actual value of the potential, but then if continues to rotate and then this arrow comes up to here, then this much will be the actually size of the potential, and then if this arrow is lying like this, then the value of the potential will be just 0, and then again it continues to rotate and then come up to here, then it will be minus, right, because it's pointing downward. Okay, this is the phasor, and in this case we are discussing the potential phasor arrow of the potential and phasor arrow of the current actually on top of each other, and they are moving together, so therefore their angle is the same, and this is why we say they are in phase. Okay, and then how about the case of the AC with capacitor? We learned that the potential in the capacitor and then the current in the capacitor, their angle is different by 90 degree, and the angle is 90 degree larger for the current, right? And then this is how we defined the capacitive reactance. Okay, so it was 1 divided by omega dc. So therefore, in the case of the direct current with constant potential, the omega is 0. So therefore, capacitive reactance will be infinitely large, which means that in the capacitor, direct current cannot go through. Okay, it's just like there is an infinite amount of resistance. Okay, and then how do we draw the phasor in this case? Now, okay, this is our potential and this is the current, as you can see. Now potential is I'm sorry, this okay, again this is potential and this is the current. Okay, phasor and arrow for the current, and current is 90 degree ahead because the direction of rotation is this direction. Okay, so they will always be in this relation. So for example, if this red arrow or red phasor of the potential comes up to this much, then this current will move together up to this much and always maintain this 90 degree relation. This is why we say that potential is 90 degree behind or current is 90 degree ahead. Okay, and then how about the case of the AC source with the inductor? In this case we learned that compared to the sine function of the potential, now current was at 90 degree lower angle. Okay, so in this case, if you use the phasor, it will look like this. You see that this is the potential arrow and this is the current arrow, and then the angle for the current is 90 degree smaller, right? Okay, in this case, again, this potential is always 90 degree ahead or current is always 90 degree behind. Okay, and this was how we defined the inductive reactance. Okay.